In the warm-up to section 3.3, I give you 4 different grids and I ask you to form 4 different connected graphs, each of which has 8 edges. So there's a lot of different possible correct answers here, but I want to point out some good answers and then some which are maybe not entirely correct, just based on my experience with doing this. People tend to make the same mistakes a lot. So first of all, I want this to be connected. And so if you were to draw something, over here I'll do some non-examples. If you drew something like this, 1, 2, 3, 4, 5, 6, 7, 8, this wouldn't work because we have this leftover vertex here, which is not connected to the rest of the graph. So remember, we said that to be connected, you need to be able to get from any vertex to any other vertex through a path. There's no way to get from this vertex to any other vertex on the graph. So this doesn't work because it's not connected. Okay, but maybe you wanted to do something like this, sort of Z-shaped graph here. So 1, 2, 3, 4, 5, 6, 7, 8. This works. So there's 8 different edges and it's connected. We can obviously get from any vertex to any other through a path. Now I want to do a different one. And I'm going to show another common mistake over here. Another common mistake is people do something like this. 1, 2, 3, 4, 5, 6, 7, 8. And this technically works, except it's really the same graph as this one. Right? Remember, the order that you draw the picture in doesn't really matter. And so this graph and this graph, they're identical to each other. If you were to label the vertices starting at 1 and going to 9, starting at 1 and going to 9, it's the same graph. They have the same set of vertices and edges. So I don't want to count this as different. Even though this is a connected graph with 8 edges, it's not different from this one. All right, to make it different, we need to make sure maybe that some of the vertices have different degrees, so I could draw something like this. This is definitely different from this graph, because this graph has a vertex of degree 8, and this graph obviously does not. Similarly, maybe you could draw something like this, 1, 2, 3, 4, 5, 6, 7, 8. This is different because it has a vertex of degree 1, 2, 3, 4, and neither of the other ones do. Or you could draw something like 1, 2, 3, 4, 5, 6, 7, 8. Maybe something like that. This has a vertex of degree 1, 2, 3, 4, 5, 6, and none of the others do. So this is 4 different graphs that are connected and that use exactly 8 edges. So just keep that in mind when we start talking about the next section. Now question 2 says a graph below represents 4 buildings on campus, and the university wishes to build bridges between the buildings so that students don't have to go outside. They don't need to draw all of the buildings, but they want to make sure that any student can get from one building to another building across some number of bridges. So essentially, we want to figure out what's the cheapest way. If this represents, say, the cost in thousands of building a bridge, what's the cheapest way to connect these 4 buildings so that you can get from any one to any other? Well, probably we'd want to use this really cheap edge right here that has only 15, a cost of only 15. We'd probably also like to use this next cheapest edge here. This bridge only costs 22. And then the next cheapest would be this bridge here from A to D, which costs 38. Right, so I'm just going to draw this out over here. If we use these 3 edges, if we build these 3 bridges, this is as cheap as you can do it, 15, 22, and 38. All right, so what we're doing here really is we're trying to find some sort of a subgraph, just like a collection of some of the vertices and edges, but not necessarily all, in such a way that everything's connected still, but as cheaply as possible. So this is getting at the idea of a tree and a spanning tree. These 4 graphs that we drew up here, these are all what we call tree graphs. So let's define what a tree is. Now, in order to define a tree, we really need to first define a cycle. So a cycle in a graph is a path whose beginning and end vertices are the same, but which does not repeat any other vertices. It doesn't necessarily have to be an Euler type cycle or a Hamilton type cycle. So you could have something like, if this was your graph, this has a cycle. I'm going to highlight it in pink. It has this cycle right here. It's a path that starts and ends on the same vertex, and doesn't repeat any other vertices. So it doesn't use them all, right? But it's sort of got a subcycle here in the middle. A tree graph is just a connected graph that doesn't have any cycles. And a forest is a not necessarily connected graph where each component is a tree. So I'm going to come back over here to these warm-up problems for a second. Notice that none of these graphs here have a cycle, right? There's no way for you to take a walk and come back to your original starting position without repeating an edge. That's what it means to be a tree, right? But it does also have to be connected. Okay, so there's some nice properties of tree graphs. In particular, a tree graph that has n vertices is always going to have n minus 1 edges. Again, looking back here, all of these graphs that we drew had 9 vertices and 8 edges. Right? Any tree graph on 9 vertices is necessarily going to have exactly 8 edges. We also have, though, that if you know that your graph is connected and you know that it has the property that it has n vertices and n minus 1 edges, then it has to be a tree graph. But that's not necessarily true if you drop the connected requirement. And we can see that in our warm-up problem. Because this was a graph that had 9 vertices and 8 edges, but it's not a tree because it has this cycle right here. This is a cycle. So this graph's not a tree, and the reason is it's not connected, right? If it had been connected, then it would be a tree based on this second property right here. And so a question that we ask a lot in graph theory is, well, how many edges would we need to delete from a graph in order to turn it into a tree? Okay, so using that property that we just discussed, we know that a graph that has n vertices and n minus 1 edges and is still connected is a tree graph. So if we wanted to delete some of these edges so that the remaining graph was a tree, we need to make sure that in the end, if it has 1, 2, 3, 4, 5, 6 vertices, it better have 6 minus 1 or 5 edges. So we need to delete edges so that there's only 5 vertices left. Well, to start with, this graph has 1, 2, 3, 4, 5, 6, 7, 8 edges. We start with 8 edges. So we're going to delete, if we want to have 5 left at the end, we need to delete 3 of them. Can we delete any 3 edges and leave ourselves with a tree graph? No, right? You can't just arbitrarily delete them. If you were to delete these 3, for example, DB, AE, and AD, the result would not be a connected graph, right? Vertex A wouldn't be connected to anything. Vertex D wouldn't be connected to anything. So you can't just arbitrarily delete graphs or delete edges, but you can delete them in such a way that the leftover graph is still connected. So for example, maybe I would delete B to C and maybe A to E, and how could I make sure that I'm still connected here? How about E to F? If I deleted those 3 edges, I would be left with A to D is still here, D to B is still here, B to F is still here, F to C, C to E. Okay, this is a tree graph, right? It's connected, it has 6 vertices and 5 edges, and it doesn't have any cycles, so it's a tree. Okay, now in practice, the reason that this comes up is in exactly the type of problem that we did in the warm-up number 2. If you have some sort of a graph and there's a cost associated to the different edges, then you might want to figure out what's the cheapest way, the minimal way of connecting these vertices. And we call that a spanning tree of a graph. So given a graph G, a spanning tree is just a tree which has all the same vertices of G, but only some and possibly all of the edges of G. So for example here, we have 3 different graphs. There's a lot of different spanning trees you could choose here. For example, you could make a spanning tree that looks like this, right, that uses A, D, B, and C. Or you could have a spanning tree that looks like this, using A to B, B to C, C to D. Or you could even have a spanning tree that looks like this, right, AD, AC, and AB. So there's a lot of different spanning trees that you can have, Keep in mind though that the result is always a tree, so it has to be connected. And it has to use all the original vertices of your graph. Okay, now in this one here, you still have a bunch of different choices, but in some sense your choices are restricted because in order to have a spanning tree, your result still needs to be a tree. It still needs to be connected. And so the only way to make sure that your graph is connected is to keep this middle edge here connecting these two triangular parts, right? Any spanning tree is going to have to keep the edge FH here. Okay, but then you could do something like this, and then maybe something like this. So this is an example of a spanning tree, right? And there's different choices you can make for the edges of the triangle that you want to keep, but you do always have to keep FH. Now in this last example here, if we want a spanning tree of this graph, it needs to have all the same vertices, so all 7 of these vertices need to remain, and some or possibly all of the edges here. Well, this graph already has 7 vertices and 6 edges. This is already a tree. We can't take anything away without disconnecting the graph. Right? If we were to delete even a single one of these edges, we would end up disconnecting some vertex from the rest of the graph. So there's only one spanning tree here, and it's the graph itself. Only spanning tree is the graph itself. Okay, so that's maybe an important note up here. I did say that to be a spanning tree, you need all the vertices of G, and you need some, but also possibly all the vertices of G. So if G is already a tree, it has only one spanning tree, and that's the graph G itself. Okay, and like we alluded to in the warm-up, we're often looking for spanning trees that have a particular property, right? If we have some sort of weight or a cost associated to the edges of the graph, we want to choose our spanning tree in such a way that it keeps cost down, right? A minimum weight spanning tree is a spanning tree in which the sum of the costs of the edges is as small as it possibly could be, right? And in a simple example like we had in the warm-up, there were only 6 possible edges to choose, and we had to pick 3 of them, and it was simple enough to do guess and check to figure out what the cheapest way to connect these vertices would be. But if you're looking at a larger example, it can be a lot harder to use guess and check, right? Imagine that the vertices instead were representing maybe a bunch of different computers on a network, and if you had 100 of them, and each one had a different cost connecting one computer to another, then it would be a lot harder to try to determine what's the cheapest way to get these all connected to each other. So as a slightly more complicated example, we'll look at this graph here, and we'll talk about an algorithm that we have to find a minimum cost spanning tree. It's called Kruskal's algorithm. It's different from, there's another algorithm that pops up a lot when you're trying to find a path that has minimal cost. This doesn't necessarily have to be a path in the end. It just has to be a tree in the end. So Kruskal's algorithm says if you want to find a minimum cost spanning tree, you need to follow these steps. First thing you do is you choose the lowest cost edge. And if there's more than one, you get to pick whichever one you like. So I'm going to come back up here, and I'm going to find the lowest cost edge. Actually, there's a few of them, right? 2 is the smallest cost out of all of these edges. There's FG, CD, and AE. They all have a low cost of 2. So this is, I can choose whichever one I want. It doesn't really matter. I'm going to choose this one. So I'm highlighting this to say this is going to be in my spanning tree at the end. I'm going to choose this to put into my spanning tree, right? I'm not cutting it out. I'm actually choosing it. Okay. Now step 2 says of the remaining edges, choose the next lowest cost edge, provided it doesn't form a cycle with the edges that you've already chosen. All right, well, my next cheapest edge would be one of the other 2s, right? Either CD or FG. I can choose whichever one I like. Doesn't matter, right? Either one you choose, it's not going to form a cycle with what you have already chosen. It's also worth pointing out, I don't need to choose an edge that's adjacent to the one that I've already chosen, or to one of the vertices on the edge I've already chosen, right? It's okay that these two are disconnected for now. This algorithm in the end is going to give you a graph that is connected. Okay, so it's okay that these are separate from each other. Okay, step 3 is just repeat. Continue to choose the next cheapest edge as long as it doesn't form a cycle. All right, my next cheapest edge is the other 2, right? The other edge labeled 2. Here it is. Okay, it doesn't form a cycle with my other pink edges that I've chosen, so I can add that in. Now my next cheapest edge. Well, I can do any of the edges labeled 3 would work, right? I could choose this one, or this one, and it's not going to form a cycle. Let's say I chose CF. Okay. Now, the next thing I would do is choose the next cheapest edge, which would be one of the other 3s. But here, we can choose this 3 here, but we cannot choose this one. If we were to choose this edge from D to F, it would form a cycle right here. Right, from F to D to C back to F would be a cycle. So what I'm going to do is I'm just going to cross this out because I know that I cannot add to this to my spanning tree anymore. Okay, but then my next cheapest edge, which I can add, is from G to I. That does not form a cycle. Okay, and then we continue. Choose your next cheapest edge. You can choose any of the 4s and it's not going to form a cycle with what you already have. So maybe I choose this one here. But once I have chosen that, I've eliminated the ability to choose E to F, because if I did, I would have a cycle E, F, C, E. Right, so I'm just going to cross this out because I know I don't want to use that. Similarly, I can choose either one of these 4s, but if I choose one, let's say GH, I cannot choose the other. I've ruled out the possibility of using this one. Now, you might have chosen HI, and then you would have had to cross out GH. It wouldn't matter in the end, it'd be the same cost in the end. Okay, and we're almost there. What would our next cheapest edge be? We've run out of 4s. Okay, so 5s. Can I put this one in? No, because that would form a cycle right here, A, C, E to A. So cross out this edge labeled 5, but I could use this one up here. Running out of pink. And I believe at this point I'm done, because in total we had 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices in the graph, and we've chosen 1, 2, 3, 4, 5, 6, 7, 8 edges. So our spanning tree has 9 vertices and 8 edges. It's connected, so it's going to be a tree, right? So here's what we have at the end. We have A to B, we have A to E, E to C, C to F, C to D, F to G, G to I, and G to H. 4, okay. Right, that's our spanning tree at the end. It doesn't turn into a path, and so that's fine, right? As long as it's connected, as long as it's a tree, then it's fine as a spanning tree. So the cost of this spanning tree would be 2 plus 2 plus 2, right? 2, 2, 2 plus, we have a 3 edge here and a 3 edge here. We have a 4 edge and a 4 edge. And then we have a 5 edge. Yep, so these are all of our edges, and the total cost of this spanning tree would be 12, 20, 22, 25. Okay. Now the nice thing about Kruskal's algorithm is it doesn't really matter which choices you make each time. Like if we had chosen this 4 instead of this 4, or if we had chosen, I don't know, this 3 instead of this 3, in the end it's still going to give you a minimum cost spanning tree. So there's lots of different spanning trees that are all minimum cost, but they should all have that same cost, whatever it is.